Hi, I'm Shyam Sadhwani, a software engineer in remote presence in Meta team. I use video calling apps like billions of users to connect to my family and friend. The audio and video quality are super important for these scenarios. Often I wondered why the quality is not as great as, let's say, Netflix streaming. I use the same network, same devices, I get very good quality during the streaming, but when I make the real-time communication call, almost feels like it could be better. Luckily, I get to work on these apps on daily basis, and we explored a lot. What are the challenges? And in this presentation, I'll be sharing what we learned, how we are mitigating those, and what we did for some of them. So before we jump onto that, let's look at the brief history of how things progressed in last decade. So if we look at some of the scenarios, for example, DVDs launched in 97, they added 1080p Blu-ray and then 4K in 2016. And YouTube, which is a streaming service, the first major streaming service, started in 2005, but they have been able to add 4K in 2010. So some of these services, they have seen accelerated growth. Now, if we look at the devices and network improved, but for real-time communication, the quality is still lagging behind. Often, one of the questions we get is, I have 1 gigabit network. I can stream 4K videos. But when I make a real-time call, the quality is blocky or it's not as great. The video is not smooth. So let's look at some of the obvious ones. Now, real-time communication calls, a lot of them are running on mobile devices and they are running on a battery. And a lot has to be done for these apps. They have to capture video, encode video, encrypt, send it over the network. At the same time, they are also receiving, decrypting, decoding, and rendering them in real time, both audio and videos. Also, there are other services running like the network bandwidth estimation. And all of this has to be accomplished in slow latency, ideally below 300 milliseconds, for a great calling experience. To do all of that on a battery and low resource usage is challenging. Also, these apps and these scenarios, they lack the luxury of server processing or any offline processing. So we drill down into some of the non-obvious ones in rest of these presentations. Now, one thing we learned was the problems and the solutions are very different when you look at two ends of the spectrum, the low-end networks and the high-end network. In this presentation, we'll be covering both of them. Let's start with the low-end network first. So there is no universal definition for low-end and high-end, and it depends from scenarios and users and the applications. What we define low-end for this presentation is the users who have below 300 kbps bandwidth. The users between 300 and 800 is like mid-end, and above 800 is high-end or HD capable networks. Now, a lot of time people get surprises that video calls are using 50 kbps or even 25 kbps these days in these network conditions. Note, this is the share that video encoders get of the overall network pipe, which gets shared between audio codecs, the signaling overhead, retransmissions, RTP overhead, duplications, and FEC. Now, the big assumption here is the bandwidth estimation, which estimates the network pipe, is working correctly. It's a complex topic on its own, which is outside the scope of this presentation. So next, we looked at what options we have for these low-end networks. Now, the biggest one which stands out is to use an efficient codec like AV1. We also looked at some of the other smaller ones like video enhancements. For example, the video scalers which come with WebRTC, they provide a reasonable quality, but they don't provide the best quality. So we improved the scalers. We also worked on the region of interest encoding. So in this one, you identify the region, which in RTC case happens to be the talking head, and we spend more bits on those. So with these ones, we saw incremental quality improvements. We are also looking at some of the advanced processing like the frame rate interpolation and super resolution. These provide significant quality, but they take a lot of resources. So what we found was the codecs is one area where we need to invest in. Let's quickly look at brief history of the video codecs. H.264 has been one of the most popular and supported codec in last decade, but it's still 20-year-old codec. Last year, Nicholas from our team, they gave a talk and he said our plans to deploy AV1. Since then, we have been able to deploy AV1 on mobile devices, but it was not easy. We hit a lot of challenges and we had to mitigate a lot of issues. But let me first explain why we chose and how we chose AV1 as the next codec. So one of the thing which surprises a lot of people is when we go and tell them that we are still using software encoders and decoders. Now what are the reasons? If you look, H.264 and even H.265 is available in most mobile devices, and it's supported in hardware which can do very low battery usage and can do 4K 60 FPS real-time encode and provide very high quality. But when we compare these codecs to do a real-time communication scenario, for example, 7 FPS or 180p and 200 kbps encoding, we found that the quality of the encoder is not as good as a software encoders. And the main reason is the prioritization. Most IHVs and hardware manufacturers are not even aware of the network conditions in which RTC calls operate even today. I'm sure things will improve, but till then we have to rely on the software codec. Hence we chose AV1. Given the licensing cost, given that it has tools for RTC scenarios, and overall quality versus performance trade-offs. Let's first look at the quality aspect of AV1. So here is a subjective quality evaluation where we are comparing AV1 at 25 kbps and 264 side by side. As you can see, AV1 is providing much better quality, less blocky, and you can see background and face very clearly. This is very important for RTC scenarios. Some of these may not be obvious in the presentation, so I have all the links in my blog. Please refer to them offline so that you can check the quality side by side. In addition to subjective, we also did the systemic quality comparison. Now, the standard method is rate distortion graphs. So in this one, the horizontal axis is the video bitrate and the vertical axis is the PSNR. What we found was when we compared AV1 to 264, AV1 outperformed 264 at pretty much all the presets. Roughly, it provided 2 dB quality improvement, or if we keep the quality same, we can reduce the bitrate by 30%. For screen sharing, we saw even more improvements, which is not surprising as AV1 has screen sharing specific tools. So now we were convinced that AV1 is better codec and probably the right choice for RTC. We needed to run public test. Before we could start public test, we hit a issue which was the binary size increase. AV1 adds 600 kilobyte to our binary. This is a significant increase as it impacts the download and install experience for people, especially on the low-end devices and networks. We analyzed the binary and we found some low-hanging fruits like the quantization tables, which were contributing about 10% of the overall AV1 codec binary. We have fixed these issues and are also working with Google to improve this on the future codecs. The other issue we were anticipating was the battery regressions. Based on our lab test, we saw around 4% battery regressions with AV1. These are very serious. A lot of RTC calls, they end because people run out of battery or people hang up once they see low battery notification like you get typically when the battery is below 20%. So in order to mitigate this, we tackled the problem several ways. First was device filtering. We filtered out the devices with low-end battery or low-end CPUs. We did codec optimization to improve the CPU performance. And the last one was we use WebRTC and STP for the codec negotiation. So we negotiate multiple codecs like AV1 and 264 upfront, and then we are able to switch the codec on the fly based on the CPU and battery levels of the devices. This even allows asymmetric codec where one side could be sending AV1 and another side could be sending 264 based on the battery levels of devices. We hit some out of memory crashes because of increase in memory usage. For this, we filtered out the devices with low end memory, but this is an area for improvement which we are also working on for optimizing the memory usage. So the next challenge we faced was how do we confirm that people or our users are actually getting high quality? For that, we needed a real-time metric that we can implement and measure the quality. We have been using composite metric, which combines things like encoding bitrate, frame rate, quantization parameters, and generates the video quality score. But this cannot be used since the quantization parameter is not comparable between AV1 and 264. PSNR is industry standard metric, but it requires the reference videos and does not work for RTC. There are non-reference based metrics which we are exploring, but they are resource intensive and are not available yet. So we had to rely on some new metrics. We came up with a scheme for this and we have been able to use PSNR for real-time communication. Now how we did this was we came up with a framework where we generate the rate distortion from the encoders caused by the compression, and we generated similar distortion caused by the scalars. These are the two main components which introduce the distortion in the sending encoding pipeline. We have been able to combine these two together to generate the final PSNR value. We verified in the lab test that the PSNR is very accurate and close enough to the real PSNR as if we had the references available. We will be sharing our findings and learnings in academic publications, but with this low complexity PSNR metric, we have been able to confirm 2 dB quality improvement when we moved from H264 to AV1. With all these mitigations, we have been able to deploy AV1 on iOS and Android devices. We have not completely replaced 264 and are working on improving the coverage, which I'll be covering later. Next, we looked at how we can improve things for the high-end network. So far, we have been talking about people with low-end networks like 3G, but a lot of people have very good networks like 5G and 100 Mbps. Just to recall, what we mean by high-end are the networks where bandwidth is above 800 kbps. Modern devices, they are able to capture 48 megapixels. And the expectations for people are to be able to get HD quality videos similar to Netflix, YouTube, or Reels. We ran some local tests. We want to provide the local camera record like quality in RTC scenarios. What we found was a bitrate of around 3.5 megabits, 30 fps video, and around 720p provides the quality at par with the local camera recordings. Now 60 fps provides much better quality than 30. The video looks smooth, but there are challenges which I'll be covering later. 1080p looks better, especially on the devices which have bigger displays, but what we found was majority of the devices people don't see any difference between 1080 and 720. Now, a lot of people wonder why is it not a simple configuration change or the camera settings change to change the encoding bit rates and to change the capture resolutions. It's not very simple, especially if you run a public test at scale with millions of devices and you collect a lot of metrics. So in the first iteration, when we ran these tests, we saw a huge regressions in talk time. We saw regression in network metrics like the packet drop rate, call drop rates, and we saw increase in robotic audio or one-star ratings, people survey results. We drill down into the reasons and mitigations. I'll be sharing some of those. So for example, one thing we learned was oscillations are really bad. By oscillations, I mean the oscillations in video quality. So these happen when users see high quality video for some time and then really low quality video. These are worse than providing a stable low quality video for majority of the users. Now to fix this, we had to modify our bandwidth estimation algorithms to build heuristics and to modify the algorithms to be able to avoid these oscillations. Other thing we learned was, as you can see in this network pipe, the higher the network bandwidth you use, you are exposing your both network adaptation and bandwidth estimation algorithms to a bigger problem space. If you use very low bandwidth, you are not going to hit any congestion. If you use higher bandwidth, you will hit more and more of these congestions and your algorithm will be tested more and more. So, for example, one thing we had to implement was ISP network throttling detection, which is not caught by the standard delay-based estimation which ships with WebRTC. Now, bandwidth estimation is an area where all of these apps they try to distinguish and they have their custom implementation for the devices and network. Other thing we learned was the audio quality matters a lot more than the video, and especially at 2.5 megabits or higher, we can afford to have 2x or 3x audio duplication on FEC to avoid any regressions in the audio quality. We found that on cellular network, we hit more of these congestions and audio regressions. So we disabled high quality modes on cellular connection. We relied on machine learning based device targeting and HD targeting, where we look at the previous call histories and are able to build heuristic whether to enable or not high quality mode at the beginning of the call. Next, we ran further iterations with these mitigations. Now, we have a lot of metrics when we run these public tests. For example, we collect performance metrics like the CPU, battery, network metrics like RTT, packet loss, and for the quality, things like video freeze, robotic audio, and video quality scores. One thing we found was regressions in battery, and they came from the camera capture FPS. Most of these regressions were not caused by increase in bitrate or increase in resolution, but from the camera capture frame rates. This is the reason we were not able to ship 60 frame FPS. Instead, we rely on 30 FPS or even go down to 24 FPS depending on the battery conditions. To mitigate some of them, we built an infrastructure where we detect things like the device model, battery level, whether devices are on cellular or Wi-Fi, and we aggregate this information. And we also do real-time monitoring, as some of these things can change during the call. And based on that, we are able to switch between a high-quality mode and the power-saving mode, whether either side is on a cellular, Wi-Fi, or these capabilities. Other thing we found was some of the devices are not able to keep up with the high memory requirements for these high quality modes. So we filtered out the devices with the low end memories. So with all of these mitigations and improvements, we were able to launch high quality HD calling experience on iOS. We are not completely done. We think there is a huge scope for improvement. Now to sum up and to recap quickly. So for the low-end network, we saw good benefits of using AV1 codec. There is a good industry momentum where iPhone 15 Pro is supporting hardware decode, Pixel 8 is supporting both encoders and decoders. We plan to leverage them. There is opportunity to use machine learning and AI to do things like video processing, video enhancement on the receiver side. Super resolution is one of them. Frame rate interpolation is another. Meta has really cool demos for the codec avatar. So these are where you build a model for human and you transmit that model once, and then during the call we are transmitting audio and we are transmitting just the video vectors instead of the full traditional encoded images, and these provide very low bandwidth video calling experiences. I have some links in my blog for some of these demos for the codec avatar. Please look at those. Now for the high-end networks, what we learned was in order to leverage the increased network and device capabilities, you have to do a lot of work. It's not as easy as just changing the setting and change the setting of network bandwidth or the camera capture frame rate. The main thing is the bandwidth estimation has to keep evolving with the improvements in the network. For this, we are leveraging machine learning based algorithms to improve our network bandwidth estimation. For the codecs, for HD and high resolution, we have to leverage hardware codecs, as the software codecs cannot be used for these more complex and advanced codecs. So We still need to use software codecs as a fallback when we hit the reliability and stability issues in the hardware, and we will keep on maintaining both of them. Most modern devices, they are adding functionality and features in the camera and video processing to distinguish and provide competitive advantage. We keep on using those, and these are one of the keys to leverage the hardware to provide better experience for the end users. So products and the infrastructure will try to make the best decision when it comes to the quality versus data versus performance trade-offs. But at the end, users need to have the final control via some settings or the UI control. Now, one thing we find is there is a huge opportunity to improve real-time communication scenario, and that lies in a good collaboration with the hardware manufacturers. The settings or the network conditions in which these calls operate today are new or unknown to the hardware manufacturers. We feel like working closely with the hardware manufacturers, if we can improve the quality for hardware encoders to work really well in these low-end networks, and especially for the newer codecs which are upcoming like AV1 and AV2, this will open up really great RTC calling experience for billions of people who are moving away from PSTN calling to the video calling. That concludes my presentation. Thank you.